Open-ended research demands constant course correction. When a single large language model tackles these multi-step investigations, it inevitably hits a structural wall. Because the work is path-dependent, a standalone agent is forced to execute every query and read every document sequentially. This linear approach creates a processing bottleneck that limits how much information the model can digest at once. As the model carries data from one step to the next, it eventually exhausts its working memory. It runs out of context window space and begins to truncate its own history, losing the very information it was sent to find. To bypass this limit, Anthropic engineered a specific organizational logic to govern how their models interact. Instead of relying on one massive sequence, they shifted to a multi-agent topology known as the orchestrator-worker pattern. Building more effective research agents relies on moving beyond sequential processing. By deploying multiple agents simultaneously, the system uses parallel context windows to navigate complex data without losing its place. Depending on the specific documentation you read, you will see this exact same architecture referred to as orchestrator-worker, hub-and-spoke, or coordinator-subagent. On Anthropic's internal research evaluations, shifting to this specific architecture yielded a 90.2% performance increase over using a standalone model. This requires a precise split in model deployment. A powerful reasoning model, like Opus 4, sits at the center to act exclusively as the lead coordinator. The coordinator then spins up cheaper, faster models, like Sonnet 4, to operate as subagents and handle the high-volume search and processing legwork. This chart shows total multi-agent performance variance. You can see that token usage alone accounts for approximately 80% of the variance between successful and failed runs. Pumping millions of tokens into a single context window yields diminishing returns. Distributing that same token spend across parallel, independent context windows generates nearly double the research performance. The industry frequently discusses multi-agent systems as peer-to-peer swarms, where individual AI agents constantly talk to each other and share a collective state. Unlike fragile peer-to-peer swarms, where errors compound rapidly, the central orchestrator topology enforces absolute stability through strict node isolation. Every decision regarding task routing, error handling, and determining the next logical step must live exclusively within that central coordinator. This creates an environment of isolated context. The subagents never inherit the coordinator's conversation history or background knowledge. Instead, every subagent receives a highly specific payload, a self-contained task description, a strict output format, and a fresh context window. Mid-task, these workers are entirely blind. They do not know other subagents exist, meaning they cannot coordinate laterally to fill knowledge gaps. If the central orchestrator omits a crucial detail during the initial handoff, the subagent simply does not have it. The entire success of the worker relies strictly on the precision of its instructions. The orchestrator manages this structural isolation through a 5-step operational loop. It begins with step 1, analyze and plan, where the lead model uses its extended thinking capabilities as a strategic scratchpad. Because context windows truncate past 200,000 tokens, the orchestrator immediately externalizes its plan into memory. In steps 2 and 3, the orchestrator decomposes the objective and spins up parallel subagent threads to act as intelligent data filters. Step 4 is aggregate and decide. The coordinator pulls back the compressed findings from every subagent and synthesizes the data. This triggers an iterative refinement loop. The coordinator actively evaluates the synthesized output, searching specifically for coverage gaps or missing context. The most effective routing heuristic here is to start wide, evaluate the initial findings, and then redelegate highly targeted, narrow queries to a fresh batch of subagents. Finally, in step 5, the system achieves sufficient coverage, exits the loop, and passes the raw findings to a specialized citation agent to ensure accurate attribution before delivering the final report. This sequence transforms a large language model from a passive text generator into a rigorous, stateful research engine. Running that full pipeline requires massive compute. System architects must embed strict scaling rules directly into the coordinator's prompt to ensure the computational effort matches the task's complexity. Simple fact-finding queries require only one agent and a few tool calls. Direct comparisons demand 2 to 4 subagents, while only highly complex research justifies fanning out to 10 or more subagents. When the coordinator does deploy a large fleet, Its most critical and highest leverage responsibility is partitioning the scope of the research. The orchestrator must assign distinct subtopics or source types to each worker, aiming for completely comprehensive, non-overlapping coverage. When partitioning fails, it breaks in two distinct directions. The first occurs when the prompt is too vague. Consider a command simply asking a system to research the semiconductor shortage. Because the boundaries lack definition, one subagent investigates the 2021 auto chip crisis, while two others blindly duplicate work on 2025 supply chains. The division of labor collapses, leaving huge gaps in the timeline. The second failure mode occurs when a broad topic is sliced into overly specific, narrow slivers. When agents are locked into microscopic subtopics, no single model owns the connective tissue between the ideas, resulting in a fractured and incomplete final analysis. Precise delegation dictates the actual ceiling of the system's intelligence. Navigating the space between vague duplication and narrow fragmentation is what makes an orchestrator effective. If routing every task synchronously through a central lead model creates an obvious processing bottleneck, it raises a critical architectural question. Why mandate central control at all? The primary benefit is observability. Forcing interactions through the hub provides full production tracing, allowing engineers to monitor interaction structures without reading private conversation contents. It also guarantees consistent error handling. Because errors and stateful agents compound quickly, centralizing control enables targeted resume from checkpoint safeguards, bypassing the need for expensive full system restarts. There is, however, one major exception to pure hub routing: the game of telephone problem associated with moving heavy data. Forcing subagents to copy full, bulky outputs like raw code or massive datasets back up through the coordinator strips away data fidelity and wastes millions of tokens. To fix this, subagents write their bulky work directly to an external file system. They then pass only lightweight metadata references back to the coordinator. Command and control logic must always route strictly through the central hub, but heavy data payloads absolutely should not. This architectural rigor carries a steep computational cost. Multi-agent deployments consume roughly 15 times more tokens than a standard user chat interface. Consequently, deploying this framework for tasks that require tight, ongoing interdependencies between agents is an inefficient use of resources. Models are not yet capable of robust, real-time coordination. This makes most standard coding tasks a poor fit, as they rarely possess truly parallelizable subtasks. You should deploy this pattern exclusively for high-value, breadth-first investigations, where the massive parallel execution vastly outweighs the operational costs. The most efficient use of the system comes from matching the architecture to the specific complexity of the task.